Imagine you are standing next to a furnace and the temperature suddenly spikes. You need your instrument to tell you that, and to tell you fast. But here's the thing. Every instrument in the real world has a delay. It doesn't respond instantly. It takes some amount of time to catch up with what's actually happening in the process. That's exactly what we are talking about in this lesson. Response time. How fast can your instrument keep up with the reality? And trust me, this isn't just a theoretical concept. In some applications, a slow instrument can be the difference between safe shutdown and a disaster. So, let's start with the basic definition. Response time is simply how quickly an instrument's output reaches the true value after the input changes. Think of it like this. Something changes in your process, pressure goes up, temperature shifts, flow changes, and your instrument needs to detect that and report it. Response time is how long that whole journey takes. Simple concept, but the way we measure it, that's where it gets more specific. On your slide right now, you will see a graph. A curve that starts low, climbs, and then flattens out. That curve is an instrument's response to a sudden change. And we use three specific terms to describe different parts of that curve. The first one is a time constant, written as the Greek letter tau. This one's very commonly used in instrumentation. The time constant is the time it takes for the instrument's output to reach 63.2% of the final value, after sudden, full step change in the input. Now, why 63.2%? That comes from the mathematics of first-order systems, exceptional behavior. Don't worry too much about the math. What matters is, one time constant gets you about 2/3 of the way there. Typically, after 5 time constants, the instrument is considered to have fully responded. That's a useful rule of thumb. The second term is rise time. Rise time is the time it takes for the output to travel from 10% to 90% of the final value. You will actually see those two dashed lines on the graph. That's exactly what they are marking. Rise time is useful because it captures the active clamping portion of the response, ignoring the slow start and the slow tail end. And the third term is settling time. This one's the most practically important for control purpose. Settling time is the total time it takes for the output to reach and stay within a narrow band around the final value. Usually that band is plus or minus 2%. Why does that last part matter? Stay within. Because some instruments will overshoot. They will jump past the final value, oscillate a bit, and then stabilize. Settling time accounts for all of that until the signal truly calms down. Now, why should you care about any of this? Well, it depends entirely on what the instrument is doing. If your instrument is part of a safety system, a trip signal, an emergency shutdown interlock, then you need it to respond fast. We are talking milliseconds to seconds. If there is a dangerous pressure buildup and your instrument is slow to respond, that interlock fires too late. That's a serious problem. On the other hand, if you are monitoring tank level for a slow, steady process, something that changes over minutes or hours, then a slow response is perfectly fine. You don't need your sensor reacting in milliseconds when the process itself is moving lazily. So, the key takeaway here is, match your instrument's response time to the speed of your process. Faster process, safety critical application, you need a fast instrument. Slow, steady process, response time is less of a concern. Let's quickly recap what we covered. Response time tells us how fast an instrument reacts to a change. We measure it using three markers. The time constant at 63.2%, rise time from 10 to 90%, and settling time, the full duration until the output stabilizes. And in practice, the right response time depends on your application. Fast for safety and dynamic process. Relax it for slow, steady monitoring. Now, we have one more lesson left in this section, and it's a concept that trips up a lot of people in the field. In lesson 8, we are going to tackle sensitivity versus resolution. Two terms that sound similar, get used interchangeably, but actually mean very different things. Once you understand the difference, you will never confuse them again. See you in lesson 8.